This is the second video for the lesson Uptown and Downtown, Exponential Equations for Growth and Decay. And this is from the topic Using Exponential Equations. You are already familiar with the general structure of exponential functions. Now we're going to dig a bit deeper and see how do we differentiate between exponential growth and exponential decay functions. So as a reminder, the general structure of exponential functions is f of x equals a times b to the power of x. Now let's see, how do we identify whether they're exponential growth or exponential decay functions? So this is the key takeaway from this video. This is what you should definitely remember. For an exponential growth function, we are looking at equations of the form y equals a times the quantity 1 plus r to the power of x. So here r is our rate as a decimal, and we are adding 1 plus that rate. So in other words, my b value is going to be greater than 1. That is how we identify an exponential growth function. For exponential decay, we are looking at equations of the form y equals a times the quantity 1 minus r to the power of x. Because we are subtracting here 1 minus our rate, 1 minus r, that is going to give us a value that is less than 1. It will still be positive, so it'll be greater than 0, but it will be less than 1. So whenever our b value is greater than 0 and less than 1, it is an example of exponential decay. Another note to keep in mind here, the a term, which is in both exponential growth and decay functions, that is always our initial value. So that is the number that we are starting with. Let's go ahead and take a look at this within the context of a couple of examples. So for number 1 here, we're looking at the population of Millville, and we are given the function p of t equals 4,000 times 1.03 to the power of t. So for this particular problem here, our a value is 4,000. And our b value is 1.03. Remember that a is simply our initial value. It has no bearing on whether this is exponential growth or decay. However, our b value will tell us that. Because the b value here is greater than 1, this is an example of exponential growth. Taking a look at example number 2, we have p of t equals 8,000 times 0.98 to the power of t, and this is modeling the population of Grand City. So in this particular case, our a value is 8,000, so that's our initial value, no bearing on whether this is exponential growth or decay. And then our b value is 0.98. That is the base being raised to the power of t, to the power of our independent variable. Because that b value is less than 1, again, it's greater than 0, it's still positive, but it is less than 1, this then becomes an example of exponential decay. So in both of these examples, we were given the functions themselves. Let's now go ahead and talk about how do we create our own functions from a specific scenario. So here we are given a set of functions over here in this box. And we're going to have to create equations for each of the 2 scenarios on the right and match them to one of the functions in that box. So let's go ahead and start off with the first scenario, which is about Blueville. It says here that Blueville has a population of 7,000. So that's our initial value, our a. And the population is increasing. That tells us this is going to be exponential growth because the population is increasing. And that is happening at a rate of 1.4%. So let's go ahead and think about our formulas here. So my function, f of x, will equal a, my initial value, which in this case is 7,000, times the quantity of 1 plus, I am adding because that word increasing tells me this is exponential growth, my rate as a decimal, so 0.014 to the power of x. Now, I don't see that function anywhere in my options here. So I'm going to try simplifying and adding what I have in the parentheses there. So now I'm going to have f of x equals 7,000 times 1.014 to the power of x. And that I do see as one of my options. So I'm going to go ahead and label that as number 1. And we'll put that as problem number 1. For problem number 2 over here, we were talking about Greenville. And we are told that it has a population of 7,000, so the same a value here, and its population is decreasing. That word tells me this is going to be exponential decay, and this is happening at a rate of 1.75%. So thinking of my function here, divide that space, we're going to go ahead and have f of x equals my a value, my initial, 7,000, times the quantity of 1 minus, since this is exponential decay, that rate as a decimal, 0.0175 to the power of x. Now, that function, as I have it written, I do see available as one of the options in my box, so I'm going to go ahead and label here that that matches with problem number 2. Thank you so much for watching.